The title of my presentation is Manufacturing Inspection with Inference on the Edge. My name is Stephen C. and I am with FLIR Systems. Here is the outline of my presentation. I will start with a brief overview of deep learning and then talk about how deep learning can be used for machine vision applications. I'll present a couple of case studies on applying deep learning to manufacturing inspection. Let's start with a brief overview of deep learning. For deep learning, it is important to distinguish between training and inference. During training, it will learn a new capability from the training data. It will take an untrained neural network model like the one circled in yellow and produce a trained model with various weights like the one circled in red. During inference, it will apply the trained model to the new data, in this case to classify an image as either dog or cat. Training is typically very computational intensive, requires a lot of training data. Training can be done locally or in the cloud, typically using GPUs. On the other hand, inference has lower computational requirement, can be done on the edge using FPGA, GPU, system on chip, etc. Recently, a new type of processor has emerged called Vision Processing Unit (VPU), which can perform deep learning inference efficiently. Convolutional neural networks (CNN) models are basically deep learning networks designed for image processing. Actually, the first CNN model, the Net5, was developed more than 20 years ago for US postal zip code recognition. The ImageNet Visual Recognition Challenge was started since 2010, where over 1.2 million training images were provided for 1,000 object categories. Here are some of the categories. For example, instead of just labeling it as a car, ImageNet provides more fine-grained labels on the type of the car, such as race car, Jeep, minivan, etc. That was the first time such a large-scale training dataset was made publicly available. Researchers can use the data to train and evaluate their object detection and image classification algorithms and compete against others in this annual challenge. All the recent winners of the challenge are CNN models such as AlexNet, VGGNet, GoogleNet, ResNet, etc. They can classify and input image into 1,000 classes with good accuracy. CNN models typically have millions of parameters and take weeks to train. For example, VGGNet was trained on 4 NVIDIA Titan GPUs for 2 to 3 weeks. ResNet was trained on 8 GPU machines for 2 to 3 weeks. What if you don't have a million training images for your application or don't want to wait for weeks of training? Fortunately, we have a technique called transfer learning, which can shortcut a lot of this work. It can take a fully trained model and retrain it for new tasks. For example, here is a network trained for task 1. We can use these layers as feature extractor by keeping the weight fixed. Then we just retrain the last layer for a new task. As there are much fewer parameters to train, it requires much less training data and it is much faster to train. One of the recent trends is towards smaller CNN models. They are more practical for mobile and embedded vision applications. They have less parameters and therefore can be trained with less training data. It requires less bandwidth to send a new model from cloud to edge as well. Many such models have been developed recently, such as GrisNet, MobileNet, etc. This table compares the various models in terms of computation, size, and ImageNet accuracy. The ones highlighted in green are much smaller and require fewer operations, but still achieve similar accuracy as the larger models. This diagram compares the various pre-trained CNN models for ImageNet in terms of accuracy, computation, and model size. The vertical axis is the ImageNet accuracy, so the higher the better. The horizontal axis is the computational requirement, so the lower the better. The circle size indicates the number of parameters, so the smaller the better. As you can see, MobileNet, circled in red, has good accuracy despite its small size and low computational need. Therefore, in the case studies that I will present later, we'll use MobileNet for transfer learning. Let's talk about machine vision applications. Deep learning is now revolutionizing the machine vision industry. Machine vision industry is shifting from traditional rule-based approach to deep learning. Traditional methods require handcraft algorithms by skilled engineers with programming and vision expertise. Deep learning can adapt to new examples without reprogramming. Tedious programming for identifying different defects is no longer necessary. For instance, instead of programming code like this, isn't it great that we can just show a bunch of good and bad examples? Deep learning is very well suited to many machine vision applications such as defect detection, inspection, classification, segmentation, etc. Textile inspection is a good example where traditional methods do not perform well after years of development, while deep learning can outperform them after a few minutes of training. In this example, the defect is detected and the zoom-in view is circled in blue here. Here are some other examples such as machine part inspection and solar panel inspection where deep learning works well. The zoom-in view of the defects detected are circled in blue here. It is very difficult to model a defect mathematically and hard to come up with an algorithm to detect any type of defects. Deep learning is highly suitable for manufacturing inspection applications. In such applications, the setup and lighting are well controlled and do not change much over time. Some setups are shown here, where ambient lighting doesn't matter and the object is always in a predictable location. As a result, relatively few training examples are needed, such as tens or hundreds of images, and the training can be done on standard laptop or desktop within minutes or hours. So, if you are interested, how do you go about applying deep learning to such applications? One approach is to make use of commercial software packages tailored to manufacturing inspection applications. They provide end-to-end solutions from image annotation GUI to training and inference tools. Examples of such software include Cognex Widi, NVTech Halcon, Adaptive Vision Studio, and so on. The other approach is to make use of open source frameworks and tools such as TensorFlow and Caffe. This is the approach we'll use for our case studies, and I will explain in more detail shortly. While deep learning is great for many applications, it shouldn't be regarded as a panacea that solves all our problems. The traditional rule-based methods are still more suitable for certain applications, such as dimensional measurement, code reading, robot guidance, precision alignment, etc. Some of those examples are shown here. Deep learning is more suitable for applications with deformable objects, variable orientation, vague specification, while traditional methods are more suitable for applications with rigid objects, fixed orientation, formal specifications. And for some applications, a hybrid approach could be used where traditional methods can complement deep learning. For example, you may use deep learning to detect where a barcode is and use traditional method to read the code. For the last part of my presentation, I'll talk about a couple of case studies for manufacturing inspection applications. In this case study, we would like to develop a deep learning solution to inspect our own camera cases, as some camera cases from our supplier could have defects, and we don't want to use defective cases in our cameras. We collected training data for three classes: good, bad, and not ready. Bad examples may include scratches, dent, logo scratches, and any other imperfections as circled in red here. Not ready means it cannot see the complete camera case or the camera case is not placed properly. Here is the workflow from training to deployment. You start with data collection and annotation. Optionally, you can augment your training data with more variation, and then run the training, which can be done locally or in the cloud. You then evaluate the model performance and may need to iterate the process repeatedly until you're happy with the performance. More training data may be needed, or some training parameters may need to be adjusted, and so on. In terms of tools, you can use open source frameworks such as TensorFlow and Caffe for the training. For deployment, you would use the trained model to run inference, and the output result could be labels for classification or bounding boxes for detection applications. For deployment platform, you can use a single board computer with an Intel Movidius neural compute stick or a FLIR Firefly DL camera. Both can run inference efficiently using the Intel Movidius VPU. In order to use the FLIR Firefly camera or the neural compute stick, you need an extra step to convert the TensorFlow or Caffe model into Movidius format using NC SDK or OpenVINO from Intel. Data collection is a key component of the workflow that could affect the model accuracy significantly. Here are some tips to improve accuracy. Training images must resemble inference images at deployment. For example, object position should be consistent. Lighting, camera, and lenses should be similar. We encounter some imaging challenges while collecting the training data. For example, some defects may be more visible depending on the camera exposure settings. Therefore, camera with sufficient dynamic range is needed to capture fine details. Moreover, lighting can help highlight certain defects. For example, some scratch can be seen under directional light, but not as clear under diffuse light. As data collection is typically very laborious, it is better to optimize the physical setup to simplify the problem, rather than trying to handle diverse conditions. The reduction of complexity allows the use of smaller network, requires less training data, and can be trained faster. With well-controlled setup and lighting for our camera case inspection, we use a mobile net for transfer learning, using relatively few training images. To speed up performance, we prune the mobile network by keeping just the first 7 layers and their weight to retain the low-level image features. We changed the last classification layer from 1000 classes to 3 classes, and we trained that layer. Using the FLIR Firefly DL camera for deployment, this proof of concept achieved inference on the edge at 24 frames per second with 97.3% accuracy. This video shows our inspection system, which can classify the cases as they move under the camera on the turntable. And the LED display will indicate a check mark for a good case and a cross mark for a bad case. In the second case study, we would like to develop a deep learning solution for PCB hand soldering inspection. Here are the two sides of the PCB board of our camera. There are 3 locations that require hand soldering where operator errors can occur: the LED light, the GPIO connector, and the RJ45 connector. We want to classify good solder versus missing or bad solder, and we need to inspect multiple regions of interest. Such inspection would be useful for quality control. For those who may not be familiar with soldering, here are some common soldering problems. Solder bridge may connect two pins unintentionally. Stray solder spatter may also connect two pins unintentionally. Other problems include lifted pad, untrimmed leads, and so on. And all of the above problems can happen on a single PCB too. For each region of interest, we collected 80 images in total, some good and some bad examples, which could be missing solder or other defects. For the LED region, here is a good example and here is a bad example where the solder is missing for all the pins. For the GPIO region, here is a good example and here is a bad example where the solder is incomplete for one of the pins. For the RJ45 connector region, here is a good example, and here is a bad example where there's a solder bridge. Here is our PCB hand soldering inspection setup. Since the region of interest are on both sides of the board, we 3D printed a carrier like this with LED ring lights both above and below so that we can put a camera above and another camera beneath the carrier to perform inspection simultaneously. For each region of interest, we use MobileNet for transfer learning, where we keep all the layers and their weight, and just modify the last classification layer from 1000 classes to 2 classes and retrain that layer. Training can be done within hours with transfer learning using a lightweight model and relatively few training data. Using the FLIR Firefly DL camera for deployment, this proof of concept achieved inference on the edge at 12 frames per second with over 95% accuracy. This video shows our prototype system. After a PCB on a carrier board has been inserted, it will indicate the inspection result using a green or red LED light for pass or fail, as circled in yellow here. We have plans to improve this further and deploy it for production use. To conclude, deep learning is revolutionizing the machine vision industry, where deep learning excels in many classification and inspection tasks compared to traditional rule-based methods. Deep learning inference on the edge is feasible, as there are smaller CNN models available which are practical for embedded vision applications. I presented a couple of case studies on manufacturing inspection, showing that deep learning is highly suitable for such application thanks to the well-controlled setup and lighting. Unlike many other applications where tens of thousands of training images are needed, relatively few training images are sufficient. Rather than training from scratch, transfer learning works well, which makes short training time feasible. For deployment, we use the FLIR Firefly DL inference camera, which combines the essential machine vision features with the power of deep learning. It is a machine vision camera with Sony Pregious global shutter CMOS sensor. It is GeniCam compliant with USB 3 vision, with support for typical features such as triggering, general purpose I/O, region of interest, etc. Most importantly, it can perform inference on the edge with the integrated Intel Movidius VPU. Being industry's first deep learning-enabled camera with best-in-class imaging performance, small size, and low price, we are pleased that Firefly received a Gold Innovators Award from Vision System Design last year. Thank you.